For over a century now, we have been able to register images of objects through photography. But even in the most modern camera, pictures are produced as a geometric representation of a three-dimensional object on a plane, which was already known in ancient times. A flat photograph imitates the three-dimensionalness of the object better or worse, depending on the lighting of the object being photographed and the background. With the invention of the laser, photography is no longer the only technique of registering images of the object. A new technique has appeared which produces true three-dimensional images and gives totally new possibilities by taking advantage of light's wave properties. Holography. This marvelous natural source of light emits radiation of a very wide spectrum. Solar light, which is received by the eye as white, is in fact a mixture of colors. In other words, waves of different wavelengths. Other sources that substitute the sun emit light of a similar spectrum. Let's turn on the laser. It emits monochromatic radiation, which in fact has one wavelength, and, what is particularly important, it is coherent light. In other words, light with constant phase relations. The expanded laser light beam is also coherent and can be presented by means of wave fronts. In a parallel beam, they are planes. If we cross this beam with another similar one, we will obtain a stationary interference region. Waves in phase cause the amplification. Waves opposite in phase cause the fading of light. Interference fringes appear, which spatial frequency depends on the angle between light beams. If we register them on photosensitive material, we shall obtain diffraction grating. When we insert this grating into a light beam, diffracted beams form with the illuminated beam the same angle as in the registration process. And what does the interference pattern of a plane wave with a wave produced by point source look like? Circular fringes appear, which form a concentric diffraction grating of a diminishing density towards the center. Let's illuminate it with a parallel beam. A converge and diverge beam appear. The converge beam forms a holographic real image of the point. The diverge beam forms a second virtual image precisely in the place where the source of light was. We have obtained the holographic images of the point. Every physical body is an aggregate of points, and each of them can be thought of as the point source of light. So if we direct the straight and reflected beams of coherent light onto a photosensitive plate, we shall record an aggregate of interference patterns, like in the case of one point. We will record the hologram of the whole object independently of its size, and complexity. Let's build an optical system for such a registration. Laser, beam splitter, lenses expanding the laser beam, mirror, photosensitive plate, and lens and mirror in the second beam illuminating the object. The photosensitive plate is illuminated simultaneously by the straight reference beam and by the light reflected from the object. The recorded interference pattern of these two beams is a hologram of the object. Here we have a somewhat extended system designed for holographic registration of large objects. All its elements must be mounted very stably. Special high-resolution photosensitive materials are used for the registration of holograms. The exposed holographic plate then undergoes photochemical treatment and drying. Let's put it into its previous place and illuminate it only with a straight reference beam. A holographic image of the object has been reconstructed. We can see it with the naked eye. It has the same optical properties as the original object. The fidelity in recording details and the complete three-dimensionalness give the impression of viewing the real object through a window. We can reconstruct the holographic image from any fragment of the hologram. It can be seen from different angles because each point of the hologram viewed the object from different angles. We already know how holographic images of three-dimensional objects are formed. Let's repeat it using a diagram. The converge wave forms one image behind the hologram. The second image appears as the extension of the diverge beam, precisely where the object was. Like the images of a single point. And what does the hologram look like? Seemingly, it is a uniformly exposed plate. Only by applying great magnification can the complicated interference structure be seen. The hologram contains so much information that each small fragment can be used to reconstruct a rather good image of the whole object. But images reconstructed from the whole hologram are of better quality and can be observed from different points. When we look with both eyes, the images are really three-dimensional. In the film, we can show this only by changing the position of the camera. The holographic image can be photographed like the real object in detail and with different focusing of the camera. The fidelity of holographic imaging was most fascinating in the early years of holography, as was later the possibility of reconstructing holograms using white light, and the successful experiments with color holography, or, finally, the possibility of holographic recording of movement. Among the many possibilities of holography, holographic interferometry has been developed and applied in practice. How does it work? If we overlap the real object and the holographic image, we shall have a common wavefront for both. If we deflect the object, interference fringes will appear. The image of the object and the deflected object itself now give two different wavefronts. The fringes are a result of the interference of these wavefronts. Holography enables the current observation and measurement of object deflections exact to fractions of a micrometer. This technique, called real-time observation, requires a very stable holographic stand and a great deal of practical experience. The hologram itself must be securely fastened and after photochemical treatment replaced exactly in its original position. Then, the real-time observation and the measurement of object surface deflections is possible. A holographic map of deflections is formed by the fringes. Without holography, this would be very difficult. A minimal change in the screw pressure gives a legible deformation image, as well as all the thermal deformations. Or ones caused by the change in humidity, showing here the defects of the base. A slight modification of the optical system allows the holographic registration of transparent objects which pass light, the so-called phase objects. In cases like this, holography produces images similar to those known in classical interferometry. We are now observing the temperature distribution of air surrounding a heated wire. Using scattered light, it is also possible to obtain three-dimensional images of phase objects. This was, of course, impossible in classical interferometry. Gas convection in a light bulb. A clear image of the phenomenon has been formed, although we are observing it through the walls of the bulb. And now an even more interesting experiment. A glass of water and a spoon of a different temperature. Unbelievable. Convection currents in pure water in an ordinary container, which is furthermore cylindrical. Classical interferometry would here be completely helpless. The technique of real-time observation is very inviting, but requires the use of an especially long time stable stand. For this reason, the technique based on double exposure of a hologram is more often applied in practice. The object is recorded in two static states, for example, before and after tightening the screw. We obtain a frozen fringe pattern as a result of the deflections of the object. The simple holographic plate holder is sufficient here. The first exposition, and after the object deformation, the second one. Here is the object we saw previously with its deflections, after tightening the screws. Thermal deflections of a piston for 3 different temperatures. The double exposure holography is often used in non-destructive testing. A plate deformed by the central force. And here is the reason for the fringe deformation, an imperceptible cut of the plate. This technique can also be used for phase objects. Here is a reconstructed image of the diffusion of two liquids. The shape of the fringes near the boundary between the liquids gives quantity information, allowing the calculation of diffusion coefficient. The emission of light by objects under investigation is no obstacle in holography. An interference filter can eliminate it. The image of ion concentration in a lamp's plasma. We already know the technique of investigating static objects. Is it possible to investigate, for example, vibrating objects? Observation of a vibrating turbine blade through the hologram of the blade gives us information about the modal shapes, but not very readable. Better results were obtained by recording a single exposed hologram during the object vibrations, analogically to photography, by photographing vibrating elements for a long exposure time. We call this a time average registration. As a result, we obtain maps of blade vibration amplitudes. This technique does not require powerful lasers and complicated optical systems. It is important to keep harmonic vibrations of the object which do not exceed several micrometers. The realization of these requirements allows us to obtain beautiful successive modes of the circular plate. The brightest regions correspond to motionless places of the plate. They show nodal lines. Periodic vibrations are the only form of motion which we can measure in this way. In other cases, the object mustn't move during the exposure time. Thus, the holographic registration of moving objects requires the application of pulse lasers. Here is the holographic system with a powerful laser. We will use this system to record a holographic portrait, because it appears that the human face is in constant movement, and the exposure time required for registration should not exceed a microsecond. We have obtained a beautiful three-dimensional holographic portrait. This one is less beautiful, since it is double exposed. In technical application, the double pulse technique is very often used. It also enables, for example, the investigation of vocal organ vibrations. And here is an experiment especially made for this film. We will observe the behavior of an object being shot through. The laser pulse is controlled by the moving bullet. We will also be able to observe the shock wave caused by the shot. And here is our hero. He is standing still, not sensing anything as yet. The bullet is still far away, but the shock wave is already approaching. Now the wave has reached our hero, but he hasn't had time to react. Finally, he reacts. And here is the bullet. It hits, producing a reflected wave, and goes straight through. Only holography allows us to witness this story. Screenplay and production, cooperation, scientific materials, and consultation. Animation, drafting, sound, management. This film was produced by the Commission of the Technical University of Łódź, in the Institute of Fluid Flow Machinery and the Institute of Applied Mechanics, and also in the Central Optical Laboratory.